So what we have got is how much current is sourced by the battery. So I can go back to my original circuit and I can define the same current Ix here with the value of 1.538 amperes. You can further see that this Ix will keep on flowing. It will reach to this node. Now it will split into two different currents. So let me call these two different currents as I1 and I2. But if you carefully observe, both the branches have the same resistance. 4 plus 5 is 9 ohm, as we had already done it here, and 1 plus 8 is also 9 ohms. So Ix will split into two equal current values. So in simple words, if I talk about I1 and I2, we will see that I1 will be equal to I2, that will be equal to Ix by 2, and Ix by 2, Ix is 1.538, by 2 is going to be nothing but 0.769 amperes. And now I can easily find out VTH. So what will be my VTH finally? To find any voltage between the two nodes, start from the second node or the second point, which is point B here, and travel up to the first point. Or in other words, start from negative polarity and travel up to positive polarity. I can go through any path I want. Let's travel like this. We will first travel through 1 ohm. You can see I2 is flowing towards node B and we are traveling from node B in the opposite direction. So the first drop, because we are traveling in the opposite direction of I2, will be positive. So it is 1 into I2, resistance into current I2. When you travel in the opposite direction, the drop is positive. Second drop will be across 4 ohm. The current through 4 ohm is I1 flowing towards node A, and we are also traveling towards node A. So we are traveling in the direction of current I1. So this time drop will be negative, minus I2 minus 4I1. But I1 and I2 are exactly same. So VTH is going to be equal to minus 2.307 volts. So that's my VTH, which is coming out to be negative. That is because we are calculating VTH between points A and B, but because of the negative value, it is concluded that point B is our higher potential than point A. So when we find VAB, which is my VTH, comes out to be the negative value. But that will not change anything. Our final answer for maximum power will remain exactly same, because power is always square of the voltage upon resistance, or square of the current into resistance. So VTH square upon 4 RTH will give us the positive value for the power. But yes, the point A is at lower potential compared to point B. So in last step, we draw the Thevenin's equivalent circuit, and this is how it will look like. Between points A and B, we bring back the RL that was connected, and the rest of the network is replaced with one voltage source VTH and one resistance RTH. Please note that I'm connecting positive terminal of VTH at point A, negative to point B, because that is what we had assumed in the beginning when we defined VAB as my VTH. But no doubt VTH came out to be a negative value, so we will mention VTH as minus 2.307 volts. So if someone wants, can connect negative towards A and positive towards B and call VTH equal to plus 2.307. That's perfectly fine. But anyways, our aim is to find P max, and the formula for P max is nothing but VTH square upon 4 RTH. So P max will not be affected by the sign of VTH. VTH is available to us. RTH is something that we had got in the previous discussion. RTH was equal to 3.26 ohms. So my final answer for P max is going to be 0.4081 watt. So that's my P max, the maximum power that will go to resistance RL.